Hello everyone, welcome back to my new YouTube video on simulation of RC low pass filter using NI-Multisim. To just give you an overview of filter, it's basically a circuit which is used to pass signals of certain frequencies and to reject signals of certain frequencies. Basically, it's filtering the signals. There are two types under that. One we call it as a passive filter, and one more it is called as active filter. Passive filter, which is made up of three basic passive components R, L as well as C, and active filter, which includes passive components. Along with that, we use an op amp to amplify or to get a gain at the output stage. So again, they are categorized into low pass filter, which will pass the signals at lower frequencies and attenuate higher frequency signals. High pass filter, that is the second one, which passes higher frequency signals and attenuates the lower frequency signals. Third one, which is called as band pass filter, which will pass a certain range of frequencies. And the fourth one, it is a band stop filter, which will reject a certain range of frequencies. So in this video, I'll be explaining about RC low pass passive filter. RC stands for resistor and capacitor because this passive low pass filter is consisting of only two components, that is R as well as C. So let me place the component over here. So one is the capacitor and one more it is a resistor. So as you can see that it is made up of only two components, and to give the input I give through a function generator. I give it to R, then from R to C, C back to the source. Now to know till what range the signal has to pass, till what frequency the signal has to pass, and from where it has to attenuate. So the frequency till which the signal has to pass, okay, so that frequency is called as cutoff frequency, and after that the signal gets attenuated. So that frequency I kept it as 200 hertz. I keep it lower frequency to design the values of R as well as C. So I have kept the cutoff frequency as 200 hertz, which means that the signals till 200 hertz has to pass, and after that it has to attenuate or it has to reject. So the formula for the cutoff frequency is given as 1 over 2 pi RC. Now I have kept an arbitrary value of R as 500 ohm. Based on this, I have found out the value of C as 1.59 microfarad. So by using that, we'll update the values of R as well as C, 1.59 microfarad and 500 ohms. Now to just see how will be the frequency response of this RC circuit, we'll go for simulate, then we'll go for analysis and simulation. In this analysis and simulation, we'll go for start frequency as 0.1, stop frequency as 100 kilohertz. You can increase the stop frequencies also. Then number of points per decade, that is 20, and the scale, the Y scale is I have kept it as decibel because it's a magnitude scale. Then output I am taking at the capacitor C1. So I have already, you can remove this also, and you can see that you have different options: circuit voltage, current. I need the output which I am taking across the capacitor C1, and the node is 2. So I'll give V of 2. Then add, it will be over here. Now we will run it. Okay, now I can see there are two plots. One is called as a magnitude plot. The second one is called as a phase plot. In the magnitude plot, we can see that up till 200 hertz or up till 100 hertz, you can see that the gain is 1, or you can see that there is no drop in the magnitude. The cutoff frequency is 20 hertz. So sorry, 200 hertz. So 100. So this is 200. So 200, there is a decrease in the gain, that is minus 3 dB reduce in the gain. And after that, you can see that the magnitude, this y-axis is nothing but the magnitude 20 log V0 by V in, and the x-axis is nothing but frequency. So this is plotted on a logarithmic graph, and your y-axis is nothing but in decibel or dB. So you can see that after this cutoff frequency, that is 200 hertz, the slope is minus 20 dB per decade. And if you're seeing the phase plot, the phase till 10 hertz or till 9 hertz, you can see that there is no change in the phase, which means there is no phase shift between the input and the output signal. And after that, it can be observed that there is a considerable change in the phase. There is a phase shift between the input as well as the output. And when you are going at around 10 kilohertz or 100 kilohertz, the phase shift is almost a 90-degree. So let us verify this using oscilloscope. So I'll close this. Then I'll place an oscilloscope, Tetronics oscilloscope over here. Then first input channel I'll connect at the input stage, and the second one I'll connect it at the output. Now double click this, switch on. Now I have to set the input frequency. I'll keep it around 50 hertz. Then amplitude I'll keep it as 2 volts. Sinusoid signal, close it. Then I'll simulate. Then instead of run, if you run again, the same frequency response plot will come. If you want over here, so I'll again go for analysis and come back to interactive simulation, then run. Okay, so this is the input and output. Now you can see that the yellow one is an input, and the blue one is output. Okay, it can be observed that there is no much phase, there is a small phase shift between the input signal and output signal, and the output signal has not attenuated. The blue one is nothing but the output signal. Stop. Okay. Now the blue one is nothing but the output signal. It can be observed that there is a little bit of phase shift between input and output. It's not 90-degree. Gradually, when you increase the frequency, you will get a 90-degree phase shift. So input is yellow color. You can see that it's 2 volt is a peak in the both the positive and negative direction, and you can observe the output, which is the blue color. There is no attenuation which is going to take place. Now what will I do? I'll again run. Then I'll increase the frequency to 100 hertz. Okay. Now again, if you can see that the magnitude is slightly decreased, but the signal has not attenuated much. Again, I'll increase the frequency to 200. That is a cutoff frequency. You can see that there is a decrease in the gain between the input as well as the output, and there is a slightly increase in the phase shift. Now above this 200, for every decade rise in the frequency, your gain will also reduce. So if I give 2000 hertz or 2 kilohertz, let us see what will be the output. I'll again run. See, it can be observed that your signal has attenuated a lot. So it can be observed 1 volt. I'll also keep. The signal has attenuated a lot. There is a loss of signal, and there is a significant phase shift. Next, again I'll increase from 2000 to 20,000 hertz or 20 kilohertz. Let us see what will be the response. Now you can clearly see that there is a loss of signal. Input is there, but output, there is no magnitude. Magnitude is almost zero. And if you are seeing the phase shift also will reduce this, and there is a 90-degree phase shift when you are going over here almost to 20 kilohertz. That is what we saw in frequency response plot. As you go till 10 kilohertz, 20 kilohertz, the phase shift also increases slightly from 0 till 90. So this is all about low pass filter, as it is also as it is already observed that till 200 hertz your frequency was your amplitude was not much lower, but as you increase the frequency, the amplitude will go down and it will almost be zero, thus proving that the higher frequency signals are getting attenuated and lower frequency signals are passed to the output stage. I hope you have liked this video. Please like, share and subscribe to my channel. Thank you.